All right. So question one, right? You're talking about mixing, the mixed state and the unmixed state. And then if the mixed state is favored at low temperatures and high pressures, okay, you are asked to draw the corresponding Venn diagram and which state has strong intermolecular forces and the justification for that. Okay. So uh, let's think about this. Okay, so we are told that it is favored at low temperatures. Okay, meaning the mixed state potential energy wise, right? Potential energy wise, the mixed state has a lower potential energy than the unmixed state. This is what it means, right? Because low temperatures favor the state with low potential energy. Okay, and then high pressures, on the other hand, favors the state with low number of configurations. So this means that the number of configurations is going to be low in the mixed state compared to the unmixed state. Right? So as a result of that, if we combine them in the Venn diagram means we have potential energy on the y-axis and number of configurations on the x-axis. The mixed state has a lower number of configurations and a lower potential energy than the unmixed state. So mixed state must be in this corner over here. You don't have to justify that, okay? It's how we come up with the Venn diagram based on the given information, right? All right. And then stronger IMFs in M or UM. So the idea is stronger the intermolecular forces, so stronger the attractive interactions between the particles, the lower the potential energy. The mixed state has a lower potential energy. Okay, therefore, the mixed state should have stronger intermolecular forces. Okay, so the justification would be the stronger the IMFs, the lower the potential energy. Okay, so this should do it because this is by definition or by convention. Okay, stronger intermolecular forces means lower potential energy. All right, now that's it for FR1. That's for easy. And then for FR2, let's see what's going on here. Okay, and you are given the two states. This time, the particular level representation of sub-microscopic representations of the mixed and the unmixed states. And then you are asked to ask two questions. Which state do you expect to be favored by potential energy? Okay, and how would you change the temperature to increase mixing of this gas with water? Okay, all right, so let's talk about this. Question one, potential energy favors unmixed over the mixed state. So potential energy favors the state with lower potential energy. Okay, so it should be the mixed state. All right, and then how do we know that the mixed state has a lower potential energy? Because you have particles closer to each other in the mixed state, meaning you can have stronger attractive interactions. Stronger the attractive interactions, the lower the potential energy. And that's why we selected mixed state being favored by potential energy. Okay, and question two, temperature change to increase mixing. Do you want to increase or decrease the temperature? Okay, those are the two options. So if you want to increase mixing, you want to lower the temperature. Okay, you're going to decrease the temperature. And why that is the case, the mixed state has a lower potential energy. Okay, so low potential energy states are favored at low temperatures. That's why you want to lower the temperature. Okay, now let's justify that. So we can write low temperatures. Low temperatures favor the state with lower potential energy. Lower potential energy. Okay, that's the main thing. And then the mixed state has a lower potential energy because you have particles closer to each other. Okay, you can write M if you want to. M has a lower, let's call it E sub P. It's fine, it's defined somewhere else. Okay, potential energy because particles are closer to each other, and they interact strongly. Okay. M has a lower potential energy because particles are closer to each other. So we can write stronger IMFs, or stronger attractive interactions between the particles. Okay, so I think those are the 2 points which I would mention in the justification. Low temperatures favor the state with low potential energy, and the mixed state has a lower potential energy because you have particles closer to each other. Okay, that should nail it. All right, moving on to FR 3. A certain mixture contains 3 substances, X, Y, and Z. The boiling temperatures of X, Y, and Z are 78, 88, and 96, okay, respectively. Rank the relative potential energies of these substances at 75 K and 1 atm pressure. Okay, so I mean, it's kind of these conditions are, kind of not that useful because we are given the boiling points. Based on the boiling points, we can have an idea about the intermolecular force strength that relates to potential energy, right? But we can appreciate the fact that at 75 K and 1 atm, they should all be in the liquid phase. So it's kind of a fair comparison in a way. Okay, anyway, so it doesn't matter. I mean, for the most part, at least. Okay, so based on this, we have the highest boiling temperature for Z. Highest boiling temperature means you have the strongest attractive interactions. Strongest attractive interactions mean the lowest potential energy or most negative potential energy. So Z should have the lowest potential energy, and then Y, and then X has the lowest boiling point, meaning you have the weakest attractive interactions between the particles, meaning you have the highest potential energy. So the correct order seems to be option C. So we would select option C as the answer. And we need to justify their answers as well. So this is 2 points and 4 points for the justification. So the idea is the relationship between the boiling point and the intermolecular force strength, and the intermolecular force strengths and the potential energy. That is what is being tested here. Okay, so we're going to start with the link between the boiling points. That is what is given to them, and then the intermolecular force strength, the immediate connection. Okay, so we're going to write the stronger the intermolecular forces, the stronger the IMFs, or attractive interactions between the particles. Let's write attractive interactions between the particles because this is coming from the particulate model of matter. Attractive interactions between the particles particles the higher the boiling point. It's not just the boiling point, melting point, density, viscosity, all of those will be higher. But anyway, this is boiling point for this particular question. Higher the boiling point. Okay, so now this means the substance with the highest boiling point has the strongest attractive interactions. Okay, so we have that, and then the other thing is the boiling point. Let me see, the stronger the attractive interactions between the particles, the higher the boiling point. I mean, students can approach this in other ways, like the what we can say, they can say that Z has the highest boiling point, therefore it has the strongest attractive interactions between the particles. Okay, so and then the stronger the attractive interactions. Okay, so I'm going to call this intermolecular forces, IMF, so it's easier to write because I don't have much space. Stronger the IMFs, the lower the potential energy. Okay, so this explains why Z has the lowest potential energy, because it has the strongest attractive interactions. Now, how do you know that? Because it has the highest boiling point, and vice versa. And then X, on the other hand, has the lowest boiling point. Therefore, it has the weakest attractive interactions. Therefore, it should have the highest potential energy. So now keep in mind that the students can convey the same idea in different ways, but this is going to be the heart of the question. The concepts are tested here. Okay. All right. Now, moving on to question 4. Let's see. All right, we're referring to FR3. X in FR3 has a relative mass of 28 AMU, while the relative mass of Y is 40 AMU. Molecular speed distribution of X and Y particles at 298 K is shown below. In the boxes provided, assign the speed distributions to X and Y and justify your answer using particular quantum of matter. Okay. All right. Now, they are the same temperature, meaning they have the same average kinetic energy. Okay. If that is the case, the particles with lighter mass must be moving faster and vice versa. So X particles have a lower relative mass, 28 AMU. Okay, meaning it should have a higher average speed. So the average speed for 2 is higher. Okay, this is the 2 average speed. This is, let's say, V2 average, and then average speed for 1 is lower. Okay, so the particles with higher average speed must have a lower mass. Okay, therefore, number 2, the second distribution must be X, and the first one must be Y. Okay, because Y is heavier, therefore it's going to be moving slower than the X particles for them to have the same average kinetic energy. That's the idea there. All right, and justify your answer using the particular quantum of matter. All right, so we need to mention few things. Okay, they are the same temperature, meaning they should have the same average kinetic energy. Okay, both X and Y have the same average kinetic energy. Let's write that. Both X and Y have the same average E sub k. So E sub k is kinetic energy. I'm trying to save some space here. Kinetic energy. Okay. Kinetic energy. Because they are the same temperature. Kinetic energy. Because they are at the same temperature. Okay. Temperature. Okay. Therefore, the lighter particles should move faster than the heavier particles. Four. I use the three dots to denote therefore the lighter particles within parentheses x must move faster. Must move faster or must be faster. Let's say must move faster. Move faster than the heavier y particles. Okay, that's it. All right, so let's explain that, and this is coming from the particular model of matter or the kinetic energy. Okay, and then last question for 5. Draw the potential. The total change in total energy versus temperature plot for the process indicated by the arrow on the diagram. Okay, be sure to label where each region occurs in your plot. Okay, so you need to make sure that you read the question carefully here. Okay, so you need to draw the plot and be sure to label where each region occurs. Okay, so you need to do both those things. All right, now this process seems to be cooling. Okay, because it's a cooling process because you're going from a higher temperature. We're starting over here and end up over here at a lower temperature. You're cooling, meaning you are removing energy from the system. Therefore, the changing energy of the system, or delta E total, must be negative. Okay, it should be below 0. And that's the first thing. And the other thing is you're starting at a higher temperature. Okay, and you're going to end up at a lower temperature. That's what cooling means, right? When you cool something, you're going to start at higher temperature and you're going to end up at a lower temperature. All right, anyway, so let's start from here. So delta E is 0 at the starting point because you haven't touched the system. And then when you cool it down, the total energy decreases. Therefore, you're going to see something like this. Okay, and then you see that at region 2, it is undergoing a phase transition. The gas is becoming a liquid because you have the gas phase here and the liquid phase here. Okay, and during phase transitions, temperature remains constant. Okay, but system will keep losing energy. Okay, why? To convert gas to a liquid. Okay, because we know at this point that the potential energy is decreasing when you go from gas to a liquid, and that's the energy that is decreased here. Okay, not the kinetic energy. That's why the temperature is constant. And once everything is converted to liquid, again the temperature and total energy decreases with temperature. Okay, so if you label the regions, okay, this is my region 1, region 2, and region 3. Okay, and then there's another part of this question, B. For each region of the dashed line, Identify whether potential energy or kinetic energy is the major contribution to the change in total energy. Okay, and briefly justify your reasoning. All right. Now, for region 1, okay, the main change occurring here is cooling, temperature change. Okay, therefore, the major contribution to the change in total energy is kinetic energy. So I'm going to write kinetic energy. So we can use this kinetic energy. Okay, why? T is changing. Okay, and region 2, T is not changing. Therefore, it should be potential energy. Okay, so the reason, the contribution, justification should be during phase transitions, temperature remains constant, but the potential energy decreases. Potential energy changes. During phase transitions, T remains constant. Transitions, T remains constant. During phase transitions, T remains constant. Therefore, kinetic energy is not changing. Therefore, K is constant. Okay, so not kinetic energy, only the potential energy is changing. And then region 3, again the kinetic energy. Why? Because temperature is changing. It's changing, and the change in potential energy is negligible. Okay, that's not the major contribution, at least. All right, so that should be it. All right, that covers the entire pre-response portion of the exam. I'll see you in class. Bye, everybody.